Hello, everyone, and welcome to a tour of Potate OS, an operating system developed in fulfillment of the requirements for CSCI E92 Principles of Operating Systems. I'm Srijesh. Today, we're going to be looking at a few items: an overview of the Potate OS, the MASH shell program, memory management, file system, the supervisor call architecture, multiprocessing, and an extra ELF utilities addition that I added to my OS. Overview of the Potate OS. This is an operating system for the Freescale TWR K70 F120M platform, which has an ARM Cortex M4 based core that supports thumb 16-bit instruction set architecture. It has a variety of devices as listed in this slide: an SD card slot, a random number generator accelerator, and our OS is going to use all of these hardware features to implement different functionalities. What's the root of this name, Potato OS? I'd love to claim that it refers to the simplicity and versatility of this OS, very much like a humble potato, but it was just an amusing pun that came to mind and the name stuck. The MASH shell. The shell is the user interface to the Potato OS. It supports 40 commands spanning a variety of functionalities like interaction with devices, files, processes, and memory. Let's take a look at a demonstration of some of the more fun and special features that the shell program offers. If we look at the shell, which is at the bottom left corner of the screen, we can see that it's quite drab and dreary. Let's add a little bit of personality through the color scheme command. The color scheme command supports a variety of themes, one of which is Skittles. Once enabled, every line will print in a different color. Fun. The shell also supports the clear and backspace functionality. When I hit clear, the console clears, giving you the prompt at the beginning of the console. We can also backspace through any number of characters like this. The shell also offers users the ability to define variables and then use them in expressions. For instance, let's define a variable called greeting with a value of hello. So now we've defined a variable called greeting with this value. Let's use it in an expression. As you can see, the variable greeting was substituted by its value hello, and the string prints after the shell interprets it. The shell also supports escape characters. Let's say I wanted to echo a long and awkward hi, something like this, with a bunch of tab characters between the H and the I. Now, all of these \t characters are going to be interpreted by the shell as tab characters to produce an output which has the appropriate number of tabs between the H and the I. The shell also features a fun command which is animated. This is the potentiometer to serial console output command that prints the value read by the potentiometer wheel that's on the K70 board and then prints it to the console. Let's take a look at that. When the argument visual is passed to this command, we can see that it renders a progress bar indicating the actual value that is read from the potentiometer. Now, if I turn the wheel of the potentiometer, we can see that the animation updates to print the correct value that's read from the potentiometer in a fun visual representation. When the value hits the limit, 255, an alarm bell is also sounded to the user. Memory management. Potato OS utilizes the external SD-RAM to use as heap memory from which clients can malloc free memset and memcheck. The memory map command prints the current allocation information. Memory is managed as a linked list of blocks with a bookkeeping header tag per block. Memory allocated is also marked with the process ID of the owning process to protect against other processes freeing unowned memory. A unique feature of Potato OS is the binned heap layout. The entire memory is split into 6 regions. The first 5 regions are comprised of equal sized blocks of 16 bytes, 64 bytes, 128 bytes, 256 bytes, and 512 bytes, respectively. The last, sixth region, is a free sized block which is used to cater to requests bigger than 512 bytes. All requests are quantized by rounding up to one of these block sizes, and the required memory is allocated from the appropriate region. The advantage of this scheme is that lookup is faster because once we identify the block size, we only need to iterate through the linked list in a particular region to allocate a free block to the user. Also, after repeated allocations and freeing, the whole sizes are uniform in a region because all allocations and freeing are done on equal sized blocks. Let's take a look at the output of the memory map command on the shell. If I type memory map, it is going to print a lot of information, including the actual region from which this block of memory was allocated. In this case, it is from the 128 byte region. The next field represents the process ID of the process that owns this memory. In this case, it is a precursor to the mash shell, which is just doing some setup for the OS as a whole. The next field indicates whether or not this memory is in use or if it is free. In this case, it is used. Next is the size of the allocation, 128. This is the same value in hex, and this is the address. File system. Potate OS supports a FAT32 file system through the removable SD card. Both reads and writes are done in units of a FAT sector, which is 512 bytes for our system. To avoid repeated SD card access, both reads and writes are cached. Cache is sized to 4 entries, i.e., 4 sectors at a time. Reading a sector populates an entry in the cache. Writes to a cached sector mark the corresponding entry in the cache as dirty. Dirty entries are also marked with the PID of the writing process. When a process reads a cached sector entry, which is marked dirty, and its PID does not match the PID that is in the sector cache's entry, then the data is fetched directly from the SD card to ensure data coherence. However, if the process that wrote to the sector in the first place tries to read the data is returned from the cache, giving it the most up to date value that's in the cache right now. Clean entries are evicted first because they can be clobbered directly and don't have to be written back, whereas dirty entries have to be written back first before they are evicted from the cache. Speaking of multiple processes, multiprocessing. The Potate OS supports multiple processes which are maintained in a doubly linked list and scheduled by a process scheduler algorithm. The SysTick timer interrupt is used to implement process switching, giving each process a fixed time quantum. Any given process can be in one of the following states: state ready, which means that it can be scheduled; state running, which means that it is currently being scheduled in this time quantum; state blocked, which means that it is out of contention for the processes that can be scheduled; and a state called marked for delete, where when the scheduler encounters a process in this state, it will close all of its open streams, free all of its memory, and effectively kill the process, unlinking it from the process list. The mash shell process with PID 1 cannot be killed by design and will persist. All other processes can be spawned, killed, and blocked. Multiprocess operation is supported through the following commands and their corresponding supervisor calls: spawn and kill. Spawn creates a new process with the passed arguments to run a specified function. All spawned processes are added to the process list with a state ready. The kill command merely marks the process whose PID matches the input with the state marked for delete, and the scheduler will clean it up when it encounters it. Block and wake. Block will block a process with a PID matching the input PID, whereas the wake command will wake up a previously blocked process. Wait blocks the currently scheduled process pending the termination of a process matching the PID of the input PID. Yield will prematurely yield the currently scheduled process time quantum. The Potate OS scheduler supports two scheduling algorithms: round robin, which iterates linearly through the process list and schedules the next ready available process, which runs for a fixed time quantum unless it returns or yields its quantum. Priority aware scheduling is a special feature of the Potate OS, which assigns a notion of priority to processes, and the processes are assigned this priority at spawn time. The scheduler then schedules each non-blocked process I having a priority pi with a probability pi divided by the sum of all priorities of the currently ready processes. This is similar to a lottery system where each process is given a number of tickets that is proportional to its own priority, and the winning process is scheduled. Therefore, this would allow for a process with a higher priority to be scheduled more than a process with a lower priority, but it will not completely starve the lower priority process because there is a chance that it can win the lottery and then have a way to be scheduled. Implementation of the priority aware scheduler. At each process switching instance, we identify all processes in the ready or running state. We sum their priorities to get a total sum priorities. We then generate a random number using the random number generator accelerator with the range 0 to some priorities. Then we divvy up the range of values between the processes, assigning to each process pi number of values, where pi is the priority of process I. Then we schedule the process in whose range the random number falls in. As mentioned earlier, this is similar to giving pi lottery tickets to each process I with a priority pi. To demonstrate the priority aware scheduler, let's take a look at the multitask underscore prio command, which I've run now. This command will spawn two processes, a high priority process that toggles the blue LED every time it gets scheduled, and a lower priority process which toggles the far right orange LED every time it gets scheduled. As we can see, because of their relative priorities, the blue LED gets to do this much more often than the orange LED. And thus, the scheduler definitely does prioritize the higher priority process in this case. However, this is also demonstrating that the scheduler does not starve the orange LED because sporadically the orange LED is also able to toggle its LED, albeit at a rate much slower than the high priority process, which is toggling the blue LED. Finally, I'd like to present the Potate OS ELF utilities. ELF is executable and linking format, and binary files of this format can be produced by the ARM toolchain compiler. Potato supports two functionalities. One, a readelf-like command to output the ELF file header and section header. A second functionality is to look for additional commands in the SD card and branch to code contained in the .text sections of these ELF files whenever the user tries to use a command that's not already compiled into the OS by default. These additional commands were implemented in C and compiled using the -fpic flag to get positionally independent code that can be relocated. This means that it doesn't have any hard-coded offsets and that we can branch to this code without having any assumptions about the position of things in the code. The binaries are stored in the SD card with a file name that matches the name of a command. When the user attempts to use this command and it isn't found in the OS by default, the SD card files are searched for an ELF file with a matching name. If the file is found, then we read the contents of the file to get the ELF file header, which is used to identify the byte offset to reach the section header table and the section header string table, which is used to resolve the section names. The section header entries are iterated over, looking at the name and comparing it to the .text string. Once the entry corresponding to the .text section is found, we read the entry, and using the byte offset and size mentioned in the entry, we read the text section into allocated memory. We then prepare input registers R0, R1 with arguments and branch and link to this newly read code where the text section will contain the instructions to execute. Let's see that in action. The readelf command, when invoked with the -h flag and the argument, which is the name of the binary which is in the SD card, we get the ELF file header. The ELF file header, among other things, contains the initial magic sequence where 45, 4C, 46 actually spell out ELF in ASCII. Also, we find the offset to the section header, which is the start of section headers, 0x2CDC. This is the byte offset from the beginning of the file to the section headers, and the number of section header entries, which is 21 in this case. We also know that the section header string table index in the section headers is at index 18. That's great. So now what are the section headers? Let's take a look at that using readelf with the -s flag. Now we get the 21 section headers, which start at the offset, which was mentioned in the ELF file header. And we see that the text section, which is the first entry, has an offset, is at an offset of 0x034, which is 52 bytes from the beginning of the ELF file. In fact, the 52 bytes are just the size of the ELF file header. The size of the text section is 100x194 bytes in hex. So using this information, we can actually read the contents of the .text section to allocated memory and execute code that it contains. Now, let's try to use the command wc. Wc is just the word count command, which is also capable of counting characters and counting new lines. So let's try that out. In this string argument, I have 3 lines which have 2 new line characters. So the output of wc-l should ideally be 2. Let's see what the Potate OS does. All right. First, it says that it's unable to find the command wc in Potate OS, but it knows that it needs to search for the command in an external elf file in the FAT file system. It found a file named wc in the FAT32 file system on the SD card, and it has branched to the code contained in the .text section and executed it to get the number of lines as 2. I would like to sincerely thank Professor Frankel for an outstanding class and providing unwavering support in the form of technical advice, debugging support, and even just motivation to push us through to ever higher peaks. TAs Alex and Stephen were invaluable, supporting us throughout through sometimes very, very extended office hours, even at the close of an extremely long day for them. My classmates were the best, very graciously helping out whenever I needed to clarify questions, yielding their own time to help me get support in office hours and otherwise. Finally, my parents, family, friends will now finally see me after the ascetic semester long sojourn. Maybe until CSCI E93. Okay? Thanks, everyone. Bye.